this tutorial, I would like to say that we'll start with something, we'll start with some beginner basics, and then we'll dive deeper into some of the more advanced topics, which some intermediate audience might like to know about. All right, so let's get started. This tutorial essentially assumes some basic knowledge of quantum mechanics, the ideas like entanglement, superposition, what that means. I'll be using Dirac notation and tensor products a lot, so I hope that people in the audience know about those. Then we'll assume these states are normalized. So I won't be showing normalization factors. Whenever I say 0 plus 1, it actually means 0 plus 1 over root 2. Then nomenclature of quantum gates, like when I say poly gates, what do I mean? When I say Clifford gates, what do I mean? Non-Clifford gates, etc. You should know what you should know the poly algebra. That means x times y equals I times z. And then what does it mean to measure a quantum operator? So spoiler, it does not mean applying the operator. Measuring a quantum operator essentially on a quantum state essentially collapses that state onto one of the eigenstates of that quantum operator. And the measurement outcome tells you something about the eigenvalue of the quantum operator. Then we need to know what parity check means. It essentially tries to check whether you are in the same eigenstate of P on 2 qubits or not. And then finally, the requirements of universal quantum computing. That means you need the Clifford group plus one non-Clifford gate to achieve universality. All right. So the very first question that we should begin with is, why do we need error correction in the first place? So quantum computing circuits that we would like to eventually harness to get some useful information or some utilitarian purposes require every operation to have an error rate on the order of 10 to the minus 9, much lower than actually 10 to the minus 9. For example, the Shor's algorithm, to perform the Shor's algorithm, you need a circuit which has much larger than a total number of 10 to the 9 gates. And that's where this restriction of being much lower than 10 to the minus 9 in terms of error rate comes about. Which means that throughout the entire computation, there's very, very, very small chance that even a single operation of yours underwent an error. And this is extremely important for the consistency of your computation. Now, state-of-the-art qubit error rates are on the order of 10 to the minus 4. And 10 to the minus 4 is actually quoting the nicer operations. So, for example, 2 qubit gates and measurements are still not quite there yet. So in order to take care of these errors, for example, there's bit flip error, which flips your bit. So your quantum bit can be in 0 or 1. And the error that takes you from 0 to 1 or 1 to 0 is the bit flip error. And then there's phase flip error, which means that the plus superposition of 0 and 1 turns into minus superposition of 0 and 1, and vice versa. So in order to take care of these errors, to get to this 10 to the minus 9 requirement, we need error correction and universal fault tolerance. That means while using qubits which can undergo an error with a probability of 10 to the minus 4, something around 10 to the minus 4, how do you achieve quantum computing circuits which do not undergo an error with a probability which is much lower than 10 to the minus 9? And thus, we begin with what error correction is now. So it's nothing but redundancy. You, instead of using a single qubit to define your logical bit value, use multiple qubit states or multiple bit states to define your logical value. So for example, here I've taken 3 bits and I'm going to use 3 bits in the 0 state to represent a logical 0 value. And similarly, I'll use 3 bits in 1 state to represent the logical 1 value. And this is what I would call the logical code space, or the assigned or chosen code space. I could choose the logical 0 value to be represented by 0, 1, 0, 1, 0, 1, whatever you want, but you have to choose a particular state and fix that for this 3-qubit state. Now, what could be the possible errors that these qubits could go through? There could be errors on the 0 state, which take you to the 1 state. So in the first row, you can see all possible single qubit errors. In the second row, you can see all possible 2-qubit errors. And in the third row, you have the one possible 3-qubit error. Similarly, the 1 logical can also undergo single qubit, 2-qubit, and 3-qubit errors. And you can see that in the error space, some of the states overlap for 0 logical and 1 logical, i.e., you can see that. I'm not sure if you can see my cursor. Could someone let me know if my cursor is visible? Okay, I'm going to assume that it's not. Okay, great. So as you can see here, you have 0, 0, 1 represented in the error space of logical 0, as well as in the error space of logical 1. So when you see a 0, 0, 1, what do you interpret? What you would do is you would rely on the probability of errors. You would rely on the fact that all of these single qubit errors are independent, which means single qubit errors can happen with probability on the order of p if a single qubit undergoes an error with probability p. 2 errors would occur with probability p squared, and 3-qubit errors would occur with probability p cubed. Now, in order for the 0 logical state to undergo an error and end up in 0, 0, 1, the probability with which this error can happen is of the order of p. However, for the 1 logical state, 1, 1, 1, to undergo an error and come to the same state 0, 0, 1, you need a 2-qubit error, which can only occur with a probability of p squared. And we know that p is less than 1. These are probabilities. So p squared would be less than p. That means the probability of the single qubit error happening and the 0 state undergoing a single qubit error and ending up in 0, 0, 1 is higher. So we would assume that whenever we see 0, 0, 1, it's more likely that an error happened while you were in the 0 state. And when you see something like 1, 1, 0, you would assume that there are more chances that an error might have occurred in the logical 1 state to have brought you here. So now for this error correction scheme to work, you need to be sure that the probability of having 2-qubit errors is fairly low. Otherwise, you would have confused something that can happen with a significantly high probability, that is 2-qubit errors, with a single qubit error, and thus your error correction scheme doesn't work. This is where the idea of how long of a bit string do you need to represent logical 0 or logical 1 is required. If 2-qubit errors are occurring with significantly high probability, that is p squared is significantly high, that means you probably need to go with a 5-bit string or 7-bit string or 11-bit string and so on. And the length of the string decides the distance of the code, that is how much protection you have against errors. If for an n-bit string in such a scenario, your distance would be n, and the number of errors that you can correct for would be n minus 1 over 2. We generally denote distance with the variable d. Okay. Now, this is something that can be done with classical bits easily, but with quantum bits, there are some issues to achieve this sort of error correction via redundancy. The very first problem is arbitrary quantum states cannot be cloned. So if you have a state psi, it can't be cloned into a 3-bit state psi with a unitary operation. So then how do you leverage any sort of redundancy if you can't actually imitate the different logical states? The way to go about would be performing something known as QND error syndrome measurement. QND means quantum non-demolition, which essentially means that you are not affecting your state while performing this measurement, essentially. So you extract some information about the state into an ancillary qubit. So you're not trying to look at your state. You're essentially just trying to extract some information about the error. And so basically what you can do is you can take any arbitrary quantum state with in this logical encoding, such that zero logical is represented by multiple qubits in the zero state, and one logical is represented by multiple qubits in the one state. And this encoding is essentially achieved with stabilizer measurements. If you measure, for example, Z tensor Z, tensor I on a 3-qubit state, it would project that state onto the first 2 qubits being in the eigenstate of Z tensor Z. And similarly, then when you measure Z tensor Z on the second 2 qubits, you can essentially collapse the state onto being in the eigenstate of these two states. So what this does essentially is that once you measure these two operators, your state, whatever product state you might have started with, would turn into an entangled state, which is an eigenstate of these two operators. And since these two operators commute, this is possible. That is, you can have a quantum state which is the simultaneous eigenstate of these two operators. And once you have that encoding established, at that point, you can just keep measuring Z tensor Z on the first 2 qubits and Z tensor Z on the second 2 qubits, and infer using the measurement outcomes whether you're in the right eigenspace or not. If, let's say, you've decided that the +1 eigenspace of these operators is going to be your logical encoding space, then whenever you get a -1 outcome, that means there is an error, and accordingly you can correct for those errors. Now, the way to go about defining a quantum encoding is as follows. You essentially, let's say you're trying to define an encoding using 3 qubits. The total number of states you can have with 3 qubits is 2 to the power 3, since every single qubit can be in one of the two states, 0 or 1. Now, what you want is that to be in an entangled state, which represents only two states in the logical basis, that is logical 0 and logical 1. So what you do is you restrict the degree of freedom of this system of 3 qubits to 2 by measuring two parity check operators, the two that I've shown you here. So now the degree of freedom after you've measured these two parity check operators would be 2 to the power 3 minus 2, 2 representing the two operators you've measured, and 3 representing the number of qubits in the system. So now you can see that the total number of degrees of freedom is restricted to 2, and that basically means that now this system can represent a single logical quantum bit collectively. So when you measure Z-type operators, it essentially detects X-type errors, that is the errors that convert 0 to 1. But you also need to correct for the errors that take you from plus to minus. When you design an encoding which protects you against errors which take you from 0 to 1, that is corrects X errors, those are called Z-type error correcting codes, or Z-type stabilizers. These are Z-type stabilizers. If a code only has Z-type stabilizers, it's a Z-type error correcting code. Now, this brings us to the second hurdle. We need to measure some information about both X and Z errors in order to correct for the various errors that can happen on a quantum bit. A classical bit will only go from 0 to 1 or 1 to 0, for example, but a quantum bit, like we've just seen, can have a phase flip error also, and multiple different errors. But the way to correct all of those different errors is to actually be able to track these two error bases, the Z errors and the X errors. We've already seen how to check for X errors. In order to check for Z errors, you might think that you can just replace those Z's with X's, but what's important is to know that you need to correct these errors simultaneously. That means when you measure those operators, the hidden logical space should not change. So the hidden logical space should actually be the simultaneous in the simultaneous eigenspace of both the X stabilizers as well as the Z stabilizers, that is the parity check operators. And this was one of the issues, like basically from the rep code example, it's not very clear how to come up with stabilizers which would be commuting and checking for both X and Z errors simultaneously. And this is basically related to the good old Heisenberg uncertainty principle that you can't measure X and Z on a single qubit at the same time and retrieve the entire information about the quantum state. Because a measurement of Z would collapse the state onto the Z eigenspace, but then the measurement of X then would be random on that state. So nothing can be inferred from these two measurements back to back. So now the question that we wanted to address for quantum error correction was that how do we come up with commuting stabilizers of X and Z type, which can correct for X and Z errors at the same time on a single logical code space. So the way to do this is, we know that X errors trigger Z type parity checks and Z errors trigger X type parity checks. So in order to correct just X errors, we need Z type rep codes. In order to correct just Z errors, we need X type rep codes. But if we wanted to correct both of these, then we want a combination of these, which is called concatenation, which essentially means the following. You first encode your 0 logical and 1 logical as such. So this is the tensor product of 3 qubit state in 0, 0, 0 and 1, 1, 1, respectively, for 0 logical and 1 logical code states. Now you define the plus logical and minus logical states as follows. That means the previous 0 logical and 1 logical, the plus superposition of those is this plus logical. And you take the tensor product of those three. That means this is a 9 qubit state, because each of these plus logical states represented here require 3 qubit encoding as shown here. So this 9 qubit plus logical dash minus logical dash is your final logical state. And then essentially your 0 logical dash 1 logical dash of the final code is given as follows. This should be not in the subscript, it should be here. So it's plus plus minus over root 2 plus minus minus over root 2. As we know, 0 and 1 logicals are plus and minus superpositions of plus and minus states. So this essentially is the Shor's 9 qubit QEC code. You detect your Z errors, your X errors by measuring ZZ on the inner encoding, and on the outer encoding, you measure the X-type stabilizers to track the Z errors. And this was basically the first error-correcting code discovered by Shor in 1995. And this was a breakthrough in the sense that before this discovery, people did not care about quantum information as much, because we knew that there will be errors in quantum states, and without a way to correct those errors, there is no way we can actually make good use of quantum communication or quantum computation. And essentially, this discovery inspired people to think about actually starting to build quantum bits, I would say. All right, so now I've shown you how what you need to measure in order to achieve a certain encoding or some information about the errors. But once you have that information, what you need to do is you need to decode the errors to interpret whether you had an X error or a Z error, and which qubit underwent this error, and where do you need to apply the correction, and so on and so forth. So the way to go about is basically rely on the good old probability of errors that I showed you on the very first slide. That is, we know that we basically assume that the probability of having a 2 qubit error is lower than the probability of having a single qubit error, and thus we can essentially come up with a maximum likelihood decoding algorithm to check which qubit underwent an error, or where do I apply the exact correction and what type of correction to get my logical value back. So with that scheme, what we can plot is this threshold plot, where on the y-axis, I would plot the logical error probability, and the x-axis, I'll plot the physical error probability. The physical error probability corresponds to the probability with which your single qubits undergo an error. This is what stands at 10 to the minus 4, on the order of 10 to the minus 4, for example. And on the y-axis, we represent with what probability does my logical state undergo an error, essentially. Sure,
Shraddha?
Yeah.
Sorry to interrupt, but there's a question from the participant. So this is the phase flip type error more visible in the Hadamard basis than in the computational basis? Or do we work enough with the superpositions that it's very visible in both?
So the Hadamard basis is your plus minus basis, right? When you apply a phase error on the 0 or 1 state, what happens? If you apply Z on 0, nothing will happen because 0 is an eigenstate of Z. Z cannot do anything to 0. Similarly, Z cannot do anything to 1. Z applied on the 1 state is just -1, and the global phase minus doesn't do anything in quantum mechanics. We ignore global phases. But if you have a superposition of 0 and 1, it doesn't have to be an equal superposition. It can be 0 plus e to the I theta 1, for example. Here, when you apply Z error on this state, 0, in front of 0, you will get no sign because it's the +1 eigen state of Z. In front of 1, you'll get a minus sign because it adds a phase of pi on the 1 state. So now your 0 plus e to the I theta 1 state has become 0 minus e to the I theta 1. And thus, the Z error actually applies some noticeable change on a superposition of 0 and 1, but not just 0 or just 1 alone. I hope that answers the question. Okay. So I'll move forward. Now, yeah, I was describing what logical error probability is. So this logical error probability is essentially the probability with which your logical code state undergoes an error. That means I have, after following my maximum likelihood algorithm, I would check whether what I decided the error is actually wrong, and another error had taken place. That would be the logical error probability. So for the 3-qubit repetition code that I showed you on the very first slides, I'm not showing you the performance of Shor's 9-qubit error correction code here. I'm just showing you what happens if the 3-qubit error correction scheme goes wrong. So essentially, the physical error probability is given by P. If the physical error probability is given by P, your logical error probability goes as 3p squared plus p cubed, which means you are bounded by 2-qubit and 3-qubit errors. Like I said, I can't correct 2-qubit and 3-qubit errors with a 3-qubit error correcting code. This was clarified in the very first slide. This is essentially just classical error correction. I'm not even talking about quantum error correction right now. So if you wanted to save yourself from 2-qubit errors, I told you that you might want to go with a 5-bit string. That means a 5-qubit error correcting code. When I do that, then as you can see, for d equals 5, that means a 5-bit error correcting code, the logical error probability actually is given by this dashed line, which is which is bounded by 10p cubed, which means 3-qubit errors can't be error corrected. Now you are safe. You're safe against single qubit errors and 2-qubit errors. Similarly, now you can go up to 7-bit error correcting code, and now you're bounded by 4-bit errors essentially, because now you can detect for 1, 2, and 3-qubit errors. So 7 minus 1 over 2 is 6 over 2. That's 3. So you can be saved against 3-bit errors. D minus 1 over 2 essentially denotes the number of errors you can correct for. Now you can see that there is some sort of phase transition here. That means below this line or before this line, that means if P is lower than 0.5, then a 7-bit error correcting code has a lower logical error value compared to a 5-bit error correcting code. And 5-bit error correcting code performs better than a 3-qubit error correcting code. But after this line, the behavior is reversed. That means the longer your string is, the worse your error correction performance. And that is actually expected. This phase transition is expected essentially because when you take more and more number of qubits, of course, you are actually introducing more ways of having errors. So for example, when I have a single qubit, the number of ways in which a single qubit error can happen is just is just 1. So the probability of an error occurring is P, of a single qubit error occurring is P. But when you represent a logical bit with 3 bits, then the number of ways a single qubit error can affect you is 3, because any of those 3 can actually flip with probability P. So there's a 3P probability that you will undergo a logical error. So essentially 3P is larger than P. However, because we are able to correct for the errors that depend on this P value, or basically order of P terms, that's why our single qubit a single qubit state actually can be protected against errors if P is low enough such that these terms are not too high, because essentially as P grows, these coefficients start to act out, and you can see that the coefficient for the very first term here is actually smaller than the coefficient for the very first term here. So if P to the 4 is large enough such that 35P to the 4 is actually larger than 10P cubed, that is when this sort of behavior will happen. That means this purple line would actually be above this green line. So what we want for quantum error correction to work is that our physical error rate is much, much below this line. And this line is essentially called the threshold line. You must have heard quantum error correction below threshold behavior. And recently, this has actually been a topic of the talk because Google recently achieved quantum error correction below threshold using surface codes. And they demonstrated that this behavior that we predict in theory for quantum error correcting codes work. So I've only shown you a demonstration, an example of a classical error correcting code here, but the Google experiment showed that this is true for quantum surface codes also. So essentially, the takeaways here would be below this threshold line, as your distance decreases, your logical error rate increases. That means as your distance goes from 7 to 5 to 3, your logical error rate would increase. I said the other way around. So over here, if your distance increases, your logical error rate increases. And over here, if your distance increases, your logical error rate decreases. So these signs are actually flipped. So what we want is below threshold behavior for quantum error correction to work. Now, this behavior relies on various aspects. It relies on how efficient your encoding is, how less of a troublemaker your errors are, but it also relies on the decoding of quantum error correction code. So we've talked a bit about how you can encode your states, and we've talked about where we lie in terms of the error or noise spectrum of qubits. Now let's talk about the different decoding schemes that we know of. So that for the repetition code that example that I showed you, maximum likelihood decoders actually work fine. That means just checking the probability with which a certain error might have happened and prioritizing that information works. However, for most codes, this algorithm is actually not tractable in classical computers. This part of your quantum computer is actually classical. Decoding happens on classical computers, and decoding using maximum likelihood right now is not tractable. There are various different methods where people are using tensor network simulations to emulate that, but until then, there are other decoding algorithms that have been actually invented to take care of the problem. So we have these are the list of different uh, decoding algorithms that have come out in the last few months. Actually, there should be a few more now, given the recent discoveries, but I haven't included them. These are basically the broader class of algorithms that you can think about. So the very first one is the lookup table or the maximum likelihood decoding that I was telling you about. Basically, you will list out all the single qubit errors, the 2-qubit errors, 3-qubit errors, and denote them probabilities, and then some combination of those errors would happen, and you would denote the probability for any any information or syndrome that you get out of measuring your stabilizers. You can basically represent various different errors via those syndromes that might have caused those syndromes. And then depending on which of those different error mechanisms occur with the maximum probability, you choose to believe that that error might have happened and apply the corresponding correction. However, this sort of tracking, like I said, is not very practical for circuit level noise decoding. That means when every operation in your circuit has some error. Now, we have something called graph-based matching decoders. These decoders are the ones that have come the closest to lookup table, in the sense that they are right now the most accurate decoders and actually the fastest decoders that exist. However, the problem with these decoders is the solution is known only for few codes, which can be represented in this um, with a graph, for example, the surface codes, color codes, etc. But codes like LDPC codes are not often represented very well with a graph, and thus the decoding of these for such codes using graph-based matching decoders can't be very efficient, or at least um, we don't know of algorithms which can actually work for these codes with a graph-based matching decoder. Now, then you have something called belief propagation, which works really well with classical error correction, but not quite with quantum error correction. These are basically iterative message passing decoders using machine learning. So the folks who are interested in machine learning should look into this kind of decoder. For a while, machine learning did not help a lot in terms of decoding, essentially because quantum error correction codes have degeneracy. That is, multiple different types of syndromes actually multiple different types of states can be error states can be represented by the same syndrome, and something of this sort causes multiple local minima propagation. When you have, we actually go with belief matching. So in recent error correction implementations, you'd see that belief matching was one of the primary choices for decoding. Then comes BPOSD. It's basically belief propagation plus some statistical post-processing. So essentially, whenever you don't have the liberty to use graph-based decoders, you can use BPOSD. This is generally slower, but works for all codes. You can use this for surface codes, color codes, LDPC codes. So all the newer LDPC code papers that you would see use BPOSD decoders. And then finally, there was this recent Relay BP paper where we've shown, from IBM, where we've shown a decoder which is actually as fast as the matching decoder for surface codes, but it works for essentially the gross codes, which is an LDPC code, and which is something that we are very excited about implementing here at IBM. So, and there was a recent implementation of this decoder on the FPGA, which essentially solves a very important problem of real-time decoding, which Google, IBM, all of us are actually working on. All right, so far I've just told you about how to protect a quantum state by encoding it into a quantum error correcting code and decoding and the restrictions about threshold, being below threshold, etc. But now we want to go beyond quantum memory. We want to be able to apply logical operations with these codes. essentially. And the most important aspect of fault-tolerant quantum computing is that you are able to apply operations that is change your logical space while tracking errors. Now, error correction preserves quantum memory. But for quantum computation, we need to make sure that while we're applying logical gates, which would require not just measuring stabilizers, but applying gates, also keeps these faults in check. Because it may happen that for applying these logical gates, you may have to apply multi-qubit gates, and these multi-qubit gates could introduce multiple errors with the same probability of order p, at which your single qubit errors were happening, and such an error would be hard to track. So we want to make sure that the logical gates that we apply, which depends on the encoding you have, does not spread these errors in a haphazard way, such that all the error correction that we intended to do has no purpose anymore. So essentially, what is very important is that a single fault should not propagate to multiple qubits, decreasing the protection of the code significantly. A less restricted version of fault tolerance would be a single fault should not propagate in such a way that increasing the distance of the code does not help. That is, your logical gates should not be such. So logical gates essentially depend on the encoding you have. If you have defined that your 0 logical and 1 logical are represented by 3 zeros and 3 ones, then in order to apply an X gate that changes 0 logical to 1 logical, you can see that you'll have to apply 3 X's, X on each of the single qubits. So now X tensor X becomes your logical X. So basically, depending on your encoding, your logical gates are decided. And what's most important is that your logical gates should not be such that they basically takes fault on a single qubit and spread it on multiple qubits in such a way that increasing the distance of the code can not protect you better from those errors. So for this, the most important requirement is, imagine you have a circuit. So intermittently, we would be doing error correction on the qubits and logical gates. I want to do some logical gate, then I'll do some error correction, then I'll do some logical gate, then I'll do some error correction, and so on and so forth. The most important requirement for fault tolerance is that the logical gate L should be constant depth with respect to distance of the code. That means the depth of the logical gate L should not rely on the distance of the code such that it increases the number of errors on this. It increases the number of errors on the circuit as you increase the distance d of the code in the same code block. All right. So basically, essentially, you don't want to increase the probability of errors with increase in the distance of the code. How do we achieve universal fault tolerant computing? So when I say universal, I mean I want to implement a universal logical gate set, i.e., I want to be able to implement logical Clifford gate set and a single non-Clifford logical gate. And note that I'm appending logical everywhere. So I think we have a question.
There's a question. Is quantum error correction decoding a part of post-processing in classical computing?
Yes. This is the post-processing you do after you get all the information. After measuring your quantum operators, you get some classical bit values as the measurement outcomes of these stabilizers, and those measurement outcomes are what you need to process on a classical processor using one of these algorithms that I actually showed you. Okay, moving on. To be able to implement transversal gates. What are transversal gates? Transversal gates essentially apply apply logical C0 in this scenario is by applying the C0 gate between different pairs of qubits here. Implementation in a single code block, as you can see, this is a depth one circuit. All these three gates can be implemented at the same time because they are not overlapping in terms of the number of qubits. So this is what I meant by constant depth. Transversal gates are depth one. Depth one is basically the best thing to do, but this is a sufficient condition. This is not a necessary condition. You could have, let's say, depth 2, but as long as it's not depth, the depth is not of the order of D, you're fine. Alternative for planar layout. So transversal gates generally don't work with planar layouts. So essentially, if you have a repetition code, you can imagine placing your qubits on the same plane, these two qubits, and then doing gates as such. But you don't have repetition codes. Like I said, we have something like Shor's or something like surface code, which are already 2D codes in 2 dimension. So in order to do transversal gates between these two two surface code patches, for example, would require you to place two chips like this and then do gates essentially in the 3rd dimension, which means a planar layout of the chip won't work. And I'm talking about planar layout because as you've seen your classical processors, your chips in your laptop are essentially 2D. So any chip we envision is generally 2D. Because of various reasons related to fabrication, etc. So if you would like to stay in 2D, then transversal gates are not quite the choice, but it's not the end of the world. If transversal gates are possible, then you can actually achieve fault tolerance via lattice surgery also, which is actually just doing these C0 gates using stabilizer measurements between two patches. So you take two patches and you try to construct some new stabilizers of the same form as these two code patches, and you do these gates. I'm not going to go into the depths of lattice surgery, but it's just to tell you that these are some local circuits which can achieve the same gates with constant depth circuits. Now, the problem is Easton-Nell theorem tells us that no quantum code can have a transversal universal set of gates. That means there will be one gate in your universal set that has to be non-transversal. And if it's not this requirement essentially flows through into lattice surgery also, because if you don't have a transversal implementation, a direct consequence of that is you don't actually have a way to implement that gate using constant depth circuits. And that's essentially where the problem of universal fault tolerance quantum computing comes into picture. We need to implement all of these gates, the Clifford group as well as the T gate. And generally, what we find is that the T gates, or basically the non-Clifford gates in the universal set, does not have a transversal implementation in 2D topological 2D local codes, or there are codes that can have transversal implementation of these. Those codes will actually have non-transversal implementation of one gate in Clifford, Clifford group, for example, the Hadamard. That's an easier problem to solve. But generally, the codes that we look at don't have a transversal implementation of the non-Clifford gates. So that brings us to the final jargon of the quantum fault-tolerant quantum error correction picture. It's basically the idea of making something called the magic state, which can be used to teleport a non-Clifford gate. So what you do is you make a state with very high fidelity, which can be used with Clifford gate sets to apply a T gate or a non-Clifford gate. This magic state, however, cannot be made fault tolerantly very easily and has basically a significantly large overhead and contributes to the significantly high overhead for, let's say, computing processing Shor's algorithm on a quantum circuit. So the problems, you might have heard that right now you need 1 million logical qubits to actually process Shor's algorithm or beat the RSA. And the reason for that, one of the reasons for that is actually preparing magic states with not very low number of qubits. So once we have logical magic states and logical Clifford generators, that gives us the universal fault tolerant. That gives us universal fault tolerant quantum computing. I'm not going into depths of any of these concepts, just so that you can have a lay of the land where universal fault tolerant quantum computing stands. Of course, none of the all of these topics cannot be covered in an hour-long lecture. So I'm just mentioning these topics such that you can familiarize yourself with these jargons if you come across them in future. So now I'm going to give you some um, insight into what approach different companies are pursuing for error correction. So the very first is Google Surface Code. It's essentially a 2D layout of your qubits. So you can see this graph. Forget the X and Z pictures for now. On the vertices lie the qubits, and these squares, the X squares represent a 4-body XXXX stabilizer, and the Z labels represent a 4-body Z stabilizer. So you're measuring a 4-qubit Z operator as a stabilizer here. And you do that for all of these qubits, and you can check that in these codes. You will always see that the X and Z stabilizers commute as required. What is the importance of surface codes? They only require nearest neighbor connectivity and planar layout, which is a huge plus for 2D superconducting chips. Then they have a matching decoder. Like I said, they have a very nice graphical representation, so the matching decoder works just fine for them. They have one of the highest known thresholds for circuit level noise, which means that they can bear significantly high probability of physical error rate compared to other codes. Now, the problem with them is they are too inefficient. One logical qubit requires d square physical qubits, where d is the distance of your code. So if you wanted to protect, for example, yourself against a single qubit error only, even then you would require an encoding which takes 9 physical qubits. And that's just 9 physical data qubits. In addition, you would need ancilla qubits, which are around 8 in number. So you need 17 qubits just to correct for a single qubit error. Google recently demonstrated this threshold plot. So the one that I was showing you was plotted in log scale, and here this is not in log scale. So as you can see that as time increases, error should increase. So this basically, the x-axis here shows you the increase in physical error probability as you go to the right. Here is your logical error probability. And this is your d equals 7. This is lower than d equals 5, and it's lower than d equals 3. Forget these two plots. These were taken from a 2023 experiment, which was not as good in terms of qubit error rates, decoding, etc. They improved all aspects of their experiment, and they were able to show below threshold QEC, that is increasing the number of qubits, you can actually protect yourself better against logical errors, because for a larger code with distance 7, which took about 100 qubits on the Willow chip, on the recently introduced Willow chip, this code actually gives you a lower logical error rate compared to the d equals 5 or d equals 3 lattice, which require lower number of qubits. So increasing the number of qubits, you can actually protect yourself better against errors in quantum states. And this was a very, very fruitful very, very important demonstration for quantum error correction. Now, Amazon, on the other hand, is going a different route of using bosonic qubits, bosonic codes to actually tackle this problem of inefficiency of surface codes. So what they do is they first, so if you remember my repetition code picture for Shor's algorithm, I had an inner encoding and then an outer encoding. Here, there is a similar scenario. You protect, you have an inner protection using something called the cat encoding, where we use a harmonic oscillator. People with a physics background would understand this better. So a harmonic oscillator is a multi-level system where you use those multiple levels to encode a logical qubit with just 2 degrees of freedom. And this is basically the cat encoding. There are various different bosonic and these types of encodings are called bosonic encodings, which use oscillators. There are different types of bosonic encodings: cat encoding, GKP encoding, etc. GKP encoding protects you against all types of errors. Cat encoding only protects you against one type of error, that is the X type of error. So you're still unprotected against the Z type of error. And to protect the Z type of error, you have an outer protection using the repetition, the classical, good old classical repetition code. So you've concatenated our what we call the discrete variable code, a repetition code, with the bosonic encoding. Here also, you are able to keep the nearest neighbor connectivity plus planar layout. However, the inner code requires 2D resonators. So if you want to have 2D chips, then we need those oscillators to be also 2D. Oscillators generally are 3D objects. So what people try to do is make them quasi 2D objects. But these have a larger footprint compared to transmons, which are the superconducting qubits, the normal superconducting qubits. Those are much, much smaller of nanometer scale, and these are of centimeter scale. They've recently demonstrated millimeter scale oscillators, but these are significantly bigger compared to normal superconducting qubits. And gates for the inner code for the cat encoding would be harder than gates for transmon, gates for just transmon. But the outer code decoding would be much easier because it's just a repetition code. So it would be much more efficient. Now, this then becomes more efficient in terms of outer code. That means a single logical qubit only requires d physical qubits in terms of the outer code, but those d physical qubits are d bosonic logical qubits, not your d physical transmons. And d here is again the distance of the code, which determines how much error you can sustain. It has been noted that repetition code might not be sufficient given that bosonic encoding, while it protects against X errors, this protection might not be enough if we want to apply gates, because the better protection you have for any type of encoding, the harder it is to do gates on that sort of encoding or qubit. So in order to make the gate operation easier, you actually give up on some level to the inner give up on some level the inner protection, and that means you need thin surface codes. That means you don't need protection for X and Z on the outer layer at this at an equal level. You need more protection for Z and less protection for X. That corresponds to something between repetition code and surface code. It's called a rectangular code, which means a 2D lattice where with a rectangular footprint. And they recently demonstrated this error correction experiment where they were able to show the total bit flip and phase flip time, which is the inverse of the bit flip logical error rate and phase flip logical error rate. I will not dive into the details of what these plots mean, but essentially, this was a good demonstration of error correction, which was concatenated with the bosonic encoding. And now finally, in the last 5 minutes, I'm going to cover what IBM has been working on. So if you take the Google Surface Code patch that I showed you initially, and then basically wrap it around in both sides, you get a torus. This is a toric code. And then introduce some extra long range connections. This gives you some weight 6 stabilizers. That means now we will go with now we are talking about a code with 6 qubit operator stabilizers. And here we need some long range connectivity. So this qubit needs some connectivity to this qubit in order to be able to measure some stabilizer between this qubit and this qubit also. That means the nearest neighbor constraint is removed. And this is a hardware challenge for experimentalists that people here at IBM are working on. This has never been demonstrated before, but the advantage of having such long-range connectivity would be that now 12 logical qubits would require 144 physical qubits for something like the gross code. And if you were going for 2 gross code, these 12 logical qubits would be given to you with a distance d equals 18. That means this with 288 physical qubits, you will be able to achieve a distance of 18. That means you will be able to correct for around 8 errors, 8 qubit errors. You can compare that with your surface code encoding. And so for example, here I'm showing you the same plot similar plot as what I showed you in the beginning for the repetition code. The x-axis is the physical error rate, the y-axis is the logical error rate. This notation is called the NKD notation. N here, that is the first number, denotes the number of physical qubits you are using. K here, that means the middle one, is the number of logical qubits. And finally, D represents the total distance. So if you take 12 logical qubits encoded in the surface code patch with distance 9, you would need 972 qubits. Similarly, if you need 12 surface code logical qubits with distance 11, you would need 1452 qubits. On the contrary, with this LDPC code with such a long-range connectivity requirement, you can encode 12 logical qubits with distance 12 with just 144 qubits. So you can compare the second one and the last one here if you wanted to, and see that there is an order of magnitude less number of qubits in total to encode a logical qubit for LDPC codes compared to the surface code. And this plot essentially shows that the error rates are pretty similar to the surface code, the green line here, and the black dots here. You can see that the LDPC codes actually perform slightly better than the surface codes, essentially because of distance 12 versus distance 11 here. But all in all, saying that by changing the encoding, I have not made the logical error rate worse, but I have reduced the qubit overhead significantly, which are both good things, because you might say that my logical error rate has become better. Sorry, my qubit overhead has been reduced, but you also have to show that the logical error rate at the same time has either become better or is the same as the surface code patches. So the problem with this is not a problem, but these types of code don't have a threshold type behavior because they are not family of increasing distance code. So in surface codes, you can say that D square physical qubits are required for distance D to encode a single logical qubit. And then you can choose the value for D. So essentially in the NKD nomenclature, this would be D squared, D squared 1D, and so on. And you can basically just pile on for D over there. Here we have just multiplied D square 1D times 12 for D equals 9. And that's what gives you these numbers here. So a threshold type behavior is related to something where you just increase D and see that the error rate goes down and down. LDPC codes have very strict NKD numbers that doesn't depend on any such variable. This is not a problem, but with this, we can just show that the logical error rate, which is more important, is actually of the same status as a surface code with similar distance. This did not have this type of code does not have a matching decoder yet, like I told you, but the relay BP decoding has shown promising results, and we've talked about this in the decoding slide. Finally, to summarize this entire talk, I would say here's the cost of fault tolerance in superconducting architectures. The black dots here resemble what number of logical qubits would be required by a surface code patch, and these circles here represent what number of qubits would be required by LDPC code patches with a certain physical error rate um, for different types of for different utilities. For example, for quantum chemistry, you're around here. For cryptography, you're around here. For classically simulable results, you're around here. It just shows that essentially the number of qubits you are able to extract using surface codes, using LDPC codes is actually better. I would recommend looking at this figure in detail in this paper to see the comparison between surface codes and LDPC codes. Given these slides, I would like to emphasize that not all is solved. There are a lot of things that we need to do better at. For example, this paper shows that in spite of lowering the qubit overhead, the time taken by the LDPC compilation of circuits is actually 10 times worse than the surface code case. And this is essentially a problem with high rate codes. Implementation of logical gates becomes harder. It's not, we are not yet sure if the compilation would not get better than this. This is an ongoing work, and this is an ongoing work. So I will leave you with these essentially these problems that we have been working on. We've been trying to make better qubits in the community, or better inner code protection with GKP codes, CAT codes, type bosonic encodings. We are also trying to make better qubits with transmons and fluxonium, and we are trying to come up with codes which can give you natural long-range connectivity, like neutral atom options, and or ion traps where swaps are pretty easy. So that gives you some sort of long-range connectivity options also. Then we are looking at different code choices, for example, surface codes, LDPC codes, bosonic encoding. And I've shown you some comparison in this talk already of how these different codes actually give different results in terms of the qubit overhead, the time, complexity, etc. Then we are also working vigorously on decoder efficiency and speed. Like I said, we did not have a good decoder for LDPC codes, but with Relay BP now we have an efficient decoder for LDPC codes. And speed of these decoders is a huge concern, in the sense that we don't, it decides the latency of your circuit. Essentially, you don't want to wait for the classical decoding to finish and incur more errors on your quantum circuit. So these decoders have to be fast in case of feedback type based circuits. Then you have some circuit compilation cost. Like I said, circuit compilation for LDPC codes right now is not that great as compared to surface codes. There have been some recent papers which actually show that it might not be the case, actually, from Qvera. And then finally, the magic state preparation cost. I did not dive deep into this problem, but magic states are some of the resource heavy components of the quantum computer, and we would like to bring the resource overhead of magic state preparation down, such that the non-Clifford operations can be done with just the same efficiency as the Clifford operations. Thank you. I can take a few questions if there are any.
Yes, so one question is, it's more of a generalized kind of question. So what is the difference between quantum error correction and quantum error mitigation?
Right. So quantum error mitigation is a technique to mitigate the effect of errors, right? To reduce the effect of errors. Whereas quantum error correction is to be able to correct those errors. So mitigation can only take you so far, I would say. You essentially try to do some sort of post-processing or some sort of feedback-based apply some feedback-based circuits such that you can mitigate the effect of errors on physical on the final outcome. But there is no encoding involved. There's no correction involved. Quantum error correction is the act of actually identifying and correcting errors and not mitigating their effect. Not just mitigating that effect. Of course, when you correct the errors, you are mitigating the effect of those, reducing the effect of those errors.
Another question is, why does the LDBC code appear to result in logical error rate having exponential dependence on physical error rate as opposed to linear in the log-log graph? They're indicating to. Yeah.
So it's not quite exponential. I would say it's more. This is not exponential. It's still linear. I would say it's linear. I wouldn't say this is exponential. It's within the error bar, whatever you're seeing here. More questions?
Yes, someone is asking about the topics of mathematics that should be known for understanding these topics.
Right. So I would say algebraic topology would be good. So if you want, there are advanced topics and there are rudimentary, like basics. So basically, you should know linear algebra well enough. Group theory, so stabilizers. The concept of stabilizers essentially comes from group theory. So group theory would be good, but not a deep dive into group theory. Once you start actually reading a basic quantum information book, you would understand what these different jargons mean. And I don't think you need extensive knowledge of group theory to be able to tackle any of these problems. But I would say linear algebra is a must. And then as you go on, things like algebraic topology, etc., come into picture. Yeah. So algebra is your friend, and then probability theory, discrete math, of course. These are some of the things that it would be nice to know, but I think a high school background of probability is just enough, and the rest is what you learn when you start to pursue quantum information anyway. But yeah, a strong background in algebra is very important.
Okay. Thank you, Shraddha, for the insightful session. Your talk gave everyone a clear picture of how error correcting codes form the backbone of reliable quantum systems. The participants, I think, really enjoyed learning since there were questions from their sides. So it was indeed a perfect start to day 2 of the Fall Fest.
Right. I'm glad I could give you some insights into quantum error correction and FTQC. There's a lot more. If you feel overwhelmed, don't worry about it. There was too much information in these slides, but I was trying to cover as many jargons as possible so that when you hear about it again, you would know where it comes from and you would know which part of this excites you most. Each of these slides actually includes something that is its own research topic. So you don't have to worry about not understanding everything or basically anything on these slides. If you were able to follow the first few slides, that's just enough. These slides were basically to introduce you with what's going on in the field right now. Okay. Well, have a good day, everyone.
Thank you. So we'll have a short break because the second talk will start from 7:30. So yeah, let's meet everyone at 7:30 again.
ये क्या सीन है? माइल क्या?
Hello, Ritijit.
Hello.
Uh, so the introduction. So for the second talk, we have Dr. Ritijit Majumdar. He is a research scientist at IBM Quantum, based at the IBM India Research Lab. He is a part of the quantum algorithm and engineering team where he collaborates with researchers using IBM quantum technologies. PhD from the Indian Statistical Institute, during which he spent a significant period as a visiting scholar at the IBM Thomas J. Watson Research Center in New York with the prestigious Fulbright Nehru Doctoral Research Fellowship. He is a recipient of the gold medal from Calcutta University for his master's degree and was honored with the esteemed DST Inspire Fellowship. So the stage is yours, Ritujit.
Hi. Thanks a lot for the introduction and thanks a lot for having me here uh, today in this Fall Fest. I'm really glad that you guys are making this such a big event and I see a lot of people are joining. So thanks a lot for doing all this. Uh, What I'll talk about today is some sort of near-term algorithms that are used for solving combinatorial optimizations. And yeah, so let's get started and we will see in the road how to get things. So is my screen visible?
Yeah, it is.
Nice. Okay, so let's get started with, as we said, that we will be talking of how to solve combinatorial optimization problems with a quantum computer. Now, whenever I say combinatorial optimization, if you are a mathematics or a computer science person, it can seem, oh, this is for me. And you can feel like if you are a physics or a chemistry person that, no, this is not really for me. I am not interested. But I'll really point out to you all that whenever we talk of combinatorial optimization, it means graph to mainly maths and CS students, and it means Ising model to physics and chemistry students. So uh, combinatorial optimization is not only for a particular branch or a particular subset of branch that you all are in. I am sure I hope at least that this will be useful for all of you here. So just to get started with that, what is the current scenario of quantum computing? If you think what is the current scenario of quantum computing? So there is a lot of myth that surrounds quantum computing. Uh, this is a picture of the quantum system one that I took in the Watson lab. So this is actually a picture of the original model here. And whenever you think of quantum computing, I don't know whether you saw this, but just a few years back during COVID, um, there was someone, I forgot the name, and it was not just some random guy. It was coming from some um, renowned industry who kind of claimed that, okay, if we did have a full-fledged quantum computer today, COVID wouldn't have happened. Now, these are kind of the myths that you keep hearing around quantum computing. That if quantum computing is here, this will happen, that will happen. So, yeah, the point is that the myth here is that whenever you have a quantum computer, it can tell the classical computer that whatever you do, I can do better than you. But the reality is very different. The reality is that You can come and tell me that, IBM has a quantum computer. I agree, but your quantum computer is broken in every possible way simultaneously. And that's true. So what do you do with that? You can do two things. You can first say that, okay, I acknowledge that there is a lot of issues with the current quantum computer. When I say issues, it mostly means noise. The quantum computer is noisy. Um, Many of the things that we do, almost all of the things that we do on the quantum computer, they are not ideal. So we can try to find uses of this broken quantum computer, and that's the current era. And so many uses have already been there, which are way beyond what our classical computers can do even today, even with this broken quantum computer. And what we look up to in the future is something that you just heard before me, is we want to fix the errors. We want to do error correction. We want to do fault tolerance. We fix the errors, and we use that for many more things. So these are the two era that we have. The current era, which we call as the utility era at this point, is where we have been able to show that even with this noisy quantum computer, even in the absence of error correction, we have been able to do we have been able to show performance beyond what a classical computer can do. But we are always looking towards the fault tolerant era. So it's the reason I am putting so much emphasis on this is that you should not get the um, feeling that, okay, the current quantum computer has a lot of issues, so I should be waiting till fault tolerance comes. If you are doing that, you are falling behind. So I just wanted to make sure you don't get that kind of message coming out of this. Now, what do we want to do? Well, using a quantum computer, we can do two things. We can get the probability distribution. Say this is a quantum circuit. For those of you who know, this is a G8Z quantum circuit. If you don't know, don't worry. We don't need this throughout our lecture. This is just for an example. This is a quantum circuit, and the output of the quantum circuit that we get from this by executing this is roughly either all 0 with 50% probability or all 1 with 50% probability, roughly. And we want to calculate the expectation value of some observables, which is used in a lot of problems. So if you think that whenever we talk of quantum computing, the first thing that comes to mind is Shor algorithm, Grover's algorithm. These are some very, very well-known algorithms in quantum computing. All of them requires the final output bits. On the other hand, there are many problems which you can cast as expectation value calculation. So when I say expectation value means, because this is probabilistic. So just like in classical computation, whenever there is a probability distribution with coin toss or say dice throwing or something, we calculate the expectation value out of that. Here also we can calculate expectation value. And when we say we calculate expectation value, it always corresponds to something called an observable. So in case you just don't know, I'm just giving a more or less overview. Those of you who know, just ignore for the time being, just stay with me. If you ask what is an observable, I can give you a circular definition. An observable is something that you can observe. What does that mean? Say you want to find out the energy of a system or something that you can measure. The mathematical correspondence of that will be an observable, and you get, when you measure this observable, you get that. If you have an energy, you want to measure energy, there will be an observable corresponding to that energy, and the eigenvalue of that observable will give you the values that you are looking for. Now, that's fine, but where do you think these observables are useful in current quantum computing? A lot of areas. I talked of energy, so immediately you can understand that if you have a chemistry problem where, say, you want to find the energy of a molecule or some excited states, some bond breaking or something that you can cast as an energy or some numerical values, you can always have an observable corresponding to that, and you can calculate the expectation value. On the other hand, if you have, say, a machine learning problem, you want to find out the accuracy. It has a it has a numerical value. So that means you can assign a observable corresponding to that, and you can have an observable whose values will give you the accuracy. Similarly, if you have a graph problem, you can think of that I want to find out some property of a graph, and that property you can encode as an observable, and the expectation value of that observable will tell you the graph property. Say you want to find out we will look into max cut today. So say you want to find out the max cut, you want to find out the mean cut, or some properties. You want to find out how many colors you need to color all the vertices with some constraint. All of these you can encode as some observable. So what we will focus on, you will see, is to for problems in combinatorial optimization, we will focus on this kind of problem where we essentially need the expectation value of some observable. And we will walk through those in steps. Now, we talked about that this is what we want to do, but what we end up doing is something like this. So as I said, that are my gates very nice? No, they have some error. So they have some noise. The gates are not perfect. Are my measurement perfect? No, they are not perfect. When I do measurement, I sometimes misread 0 as 1 and 1 as 0. You can even ask that, okay, the qubit is sitting idle here. Is that perfect? No, it's not also perfect. When the qubit is sitting idle, it has a tendency to release energy and go down to the ground state. So all of these taken into consideration, what ends up happening is we were supposed to get all 0 and all 0 or all 1 with 50-50 probability. We end up getting some other values as well. So when we calculate the expectation value, we end up getting something which is slightly off from here, right? So one of the things that is done in current or has been done for a few years now is that we understand that running a very big quantum circuit is difficult because of this noise issue. We will end up with a lot of noise if you have a really big quantum circuit. So the question that was asked is, the classical computer, you see, they are good at doing a lot of things already. So, for example, if any of you come and tell me that I have designed a quantum sorting algorithm, my reaction will be, okay, good for you, go and have fun. Because we already have classical algorithms which are very, very efficient in doing sorting. Why do you need a quantum algorithm for that? So similarly, these things were decided that we can actually break the entire workload into quantum and classical portions. There are portions of a given workload. So when I say a workload, an algorithm has multiple steps. Some of the steps a classical computer can already do very well. No point in trying to find a quantum equivalence of that. On the other hand, there are certain steps where quantum can actually, where you can benefit by using quantum. So we end up with something called a hybrid quantum classical algorithm. And this is what we will focus on today. Some part of the algorithm will be quantum and some part of the algorithm will be classical. These problems that we will talk about today, and you will hear a few more over this week for different types of hybrid quantum classical algorithms. What we will focus on is something that we call as variational algorithms. Here, the idea is, okay, let's look into variational algorithm with this particular example that we want to brew the perfect coffee, quantum coffee. Okay, so we want to brew a perfect coffee and think of a scenario where, say, you are having the fall fest and someone is attending there in person, and that person is a very bad guest, but you are trying to be a very good and tolerant host, right? So we are in that scenario where you want to give them some coffee, and you have this coffee, you have prepared this coffee, you give it to that guest and ask that, sir, do you like this coffee? The guest says it can be better. Okay, what will be the natural question that you will ask next? That, okay, if you so just tell me, like, maybe the sugar is more, the sugar is less, I can give more sugar, less sugar, you want more coffee, you want less coffee, more milk, less milk. I mean, just tell me what you want here. This is what you will ask naturally, right? If the guest tells you that it can be better, that tell me what I should add or remove from this. And here is why the guest is very bad. The guest now comes and says, no, I am not going to tell you what I need, but I don't like this coffee. It can be better. So what can you do? Think of what can you do here. You can do two things. The first thing that you can do is you can say, भाड़ में जाए, नहीं पिलाना है आपको coffee. You go and have whatever you want. If you are not even going to tell me what you need, I don't care if you have coffee or not. That will be a very valid answer if any one of you were thinking that this is what I should be telling this guest. But let's think that there is a this host is very tolerant and they are trying to be very good. They are trying to respect the guest. And so what can we do now? See, if the host is not going to tell me what more or less this coffee needs, we can just try out different things and keep asking feedbacks from the host, right? This is the only thing that we can do at this point. So we can add more sugar. Say the host goes and adds more sugar, prepares a new cup of coffee where he adds more sugar than the last time and asks, sir, is it better now? The host says, this is worse than before. So what you realize from here is that this guy does not like more sugar, right? So you will say, okay, let me go back, prepare a new cup of coffee where I'll add less sugar, I'll add more coffee. Now you go and do the same thing. You ask the host that, sir, I have prepared a new cup of coffee for you. Is it better now? He says, yes, this is better than your last attempt. So what you realize is, okay, I should be adding less sugar. I should be adding more coffee. Maybe I can add more milk. So the thing that we are doing at this point is something like a trial and error. We add or remove some ingredients. We prepare the quantum coffee. This is the quantum part. And as you can understand that adding this less sugar, more sugar, these are basically classical, and asking the host whether they like it or not. These are basically classical, where the coffee here is quantum, as you can understand from this cue. Um, so you add or remove an ingredient, you prepare the coffee again, you go and ask the host whether they like it better or not. If yes, you keep that ingredient and you add or remove something else. If the guest said that no, this is not better, this is worse than before, you remove that ingredient and you repeat this. You keep repeating this for many times, and you can expect that the host will start liking the coffee. I mean, either it will be the perfect coffee in the world, or the host will say that, okay, this is good enough. I don't need any better. So you can give it to me. That is precisely what a variational algorithm is. We start with a trial solution that we call as an ansatz, and we let call this psi of theta, where theta is a set of parameters. It's a vector of parameters. Say there are multiple unknown variables. Like you can think in terms of the coffee making. Say this is the amount of coffee, this is amount of sugar, amount of milk, and so on. So we don't know how much we need to put each of them to make the perfect coffee. So there are m unknown variables here. How do we guess this trial solution? It can come from domain knowledge or heuristically. If you are going for things like chemistry, physics, so we have, say, UCCSD answers for chemistry, we have QAOA for optimization, or if you think of, say, machine learning, efficient SU2 kind of thing, these are just heuristic. Even in chemistry, we have heuristic hardware efficient answers and things like this. So we can get this trial solution either by some domain knowledge or from some heuristic. And then we go ahead and calculate the expectation value of this trial. So the expectation value you can think of as the feedback from the host. Do you like it better than last time, or worse? Is it worse than last time? So that particular feedback is the expectation value here. And once you get the expectation value, you create a new set of parameters. And for this, many classical algorithms exist. How do you create a new set of parameters? Um, The example, if you can think that the type of example I was giving you, you try to increase sugar, you get a feedback. If you realize this is not, I mean, the host is saying this is a worse, this is actually worse, then you reduce sugar, try increasing something else. This is kind of the way Kobila algorithm works, but there are many other algorithms as well that you can use. You create a new set of parameters and then you repeat the steps 1 to 5 till some convergence, till you get the perfect value, or the host says that this is good enough. You don't have to try anymore. So this is kind of how a variational algorithm works. And what we will look at today is, for optimization, this particular algorithm called QA. So let's dive into this hybrid quantum classical algorithms, but now specifically for combinatorial optimization. But what I will urge you, as I said before, that if you understand the way QAOA is going to work, if you understand the steps of the QAOA, then it should not be very difficult to use the same thing for chemistry, the same thing for machine learning. It's mostly that the way the circuit creation, like QAOA is a particular way of creating the answers. The answers creation will change from domain to domain, but otherwise, if you understand the working principle of the entire algorithm, you should be able to go ahead and use this for other domains as well. Okay, let's get started with this. And the first thing that you should be doing whenever you are working on any quantum algorithm, any quantum workflow, in fact, the best thing to do is to break it down into these 4 steps, which we call as Qiskit pattern. The first step, and we will see this. The first step is, say when I am saying that you have a machine learning problem, you have some cat and dog images, and you want to have a quantum machine learning model that will be able to distinguish between cat and dog. All of these words are very nice. I understand what I say. You understood what I say. A quantum computer doesn't understand what are cats and dogs, and what do you mean by classification of that. And this is even true for classical algorithms. I mean, classical computers, right? They understand bits. They don't understand cats and dogs. But quantum computers speak a different language, even from a classical computer. So the first step that we need to do is to map a problem into the language that a quantum computer understands. And that's quantum circuits and operators, which are basically observables. So this is step 1 of Qiskit pattern, and often this is the main research area that you have. Whenever you think of a problem you want to solve, you first need to come up the with how to actually map that problem into the language that a quantum computer will be able to understand. And how to do that mapping, there is no straightforward way to answer this. This is often the main research area that you will go and find whatever problem you want to solve. Once you have this done, you need to optimize the circuits for target hardware. So you came up with some circuits. They may not be very good circuits, but you can now optimize the circuit and everything. There are already existing methods to do that, but see that there are always scopes that who said that the existing methods are the best methods, right? There is always a scope of research here also, that say I have a general algorithm that works for all problems. Maybe it is possible to have a specialized algorithm that will work particularly well for your problem. Or you can even say that, okay, you have a generalized method to do that. I can improve over that method. So all these kind of research is also there. But why is it good to break it down into patterns? See, the first step when you are mapping the problem into the language of quantum computer, you don't need to worry that this language, whether these circuits are optimized or not, that is not what you should be focusing at this point. You just need to focus on how do I, from the equations and everything, how do I create the quantum circuit? That should be your main focus. What should be my observable? This should be your main focus. So breaking this down actually helps you in putting the focus in the right point. Once you have done that, now if you want, you can go and say, okay, can I even optimize my circuits better? Once you have done that, we execute it on the target hardware. The outcomes again are some zeros and ones. That is not the result of your machine learning problem. You need to map it back into what you are trying to do, say classification or something. So that is kind of the post processing. This is a very natural workflow. There is nothing very novel about this workflow. But in general, we don't break down a problem like this. It is always advisable and a really good practice to break down any problem you have into these 4 steps. Focus on only one step at a point without worrying about the other steps. What we will focus on today is step 1. You can go and see in the IBM Quantum Learning platform. There are already existing tutorials that shows you how to do step 2, 3, and 4. But we will try to understand how to do this step 1 here. So coming to combinatorial optimization, what are combinatorial optimization? Maybe many of you know, but in case some of you don't, I won't go into too much of a technical definition, but you can think of that there is always a cost function that we want to maximize or minimize. And this cost function is a function of x, which can be a vector, and you want to do some assignments of x such that your cost function is either maximized or minimized. Examples. Examples always make things clear. Knapsack is a very famous problem where the thing is that, say, I have gone to your house and I have a bag with me. I see many valuable things in your house and I want to steal some of them. Now, of course, I cannot steal everything in your house because there is only a certain amount of things that can fit in my bag. So the question is, what are the items that I should select so that my robbery was successful? So what I mean is that, say your home, maybe you already have a laptop and you have a few water bottles. Of course, your laptop is more valuable than 2 or 3 water bottles. So if I want to steal, it makes more sense to steal 1 laptop than 3 water bottles. So only counting the number of items that I have been able to put in my bag is not sufficient. So here, the total value of items is something that we want to maximize. And if we select that item, we put x equal to 1. If we don't select that item, we put x equal to 0. This is a very classic problem that's called knapsack. Similarly, we can have vehicle routing problem, like you want to go from one point to another. You want to minimize the total distance traveled, and there is traffic in this, something that Google Map keeps doing every day. We have job scheduling problems that, say, the organizers of the fall fests are facing at this point, that they have many speakers, and maybe someone says that I am available now, someone says I am not available at that point. So how do they accommodate all of them properly? Right? This is a very hard problem. And that's kind of a job scheduling problem here. Maybe for Fall Fest, we can say speaker scheduling problem, but anyway, the generalized thing is job scheduling problem. And all these problems are very hard problems. So they are very hard problems. When we say very hard, these are NP hard problems. And if there are, the way I like to think of NP hard problems is that if there are students of maths or computer science, please don't get too angry on me for saying it like this. If they are NP hard problems, perhaps you should not spend too much time trying to find polynomial time solutions of those. Yeah, as I said, if there are mathematics or CS students, they can get very angry with this kind of definition. But roughly speaking, these are very hard problems for which we don't have any polynomial time solution. What we do here, and this is actually something very important, is do we use a quantum computer to try to find the best solution? See, if I can do that, what it would mean is, since most of these combinatorial optimization problems are NP hard, which again, non-technically speaking, don't just quote me anywhere, people will get very angry, is these are some of the hardest problems in the class NP, right? So if I can solve any one of those problems in polynomial time, then everything in the NP hard problem can be, in NP hard class can be solved in polynomial time, and then P becomes equal to NP. So We don't. When the first time this combinatorial optimization was approached using QAOA, the goal was not to prove P is equal to NP and go for a filled medal or something. But often, what we do, we miss out a good enough solution when we target the best solution. So this is the same thing that is done in combinatorial optimization. We recognize, we acknowledge that getting the best solution is very hard. So why not settle for a good enough solution? And how is good enough solution defined? It is usually defined as a ratio of what you have obtained versus the optimal. There are ways you can ask, how do I find the optimal? There are ways you cannot directly find the optimal, but there are ways you can give a bound on this ratio. And um, you want to achieve an approximation ratio as high as possible if it is a maximization problem. Right? If you if you get it one, then you have got the best result. Um, This is what we will do for quantum also. We are happy to settle for approximate solutions. What we can hope is there are still no proofs that this is going to happen, but what we can hope is either we find better approximation ratio than classical, or we find similar approximation ratio faster than classical. So if either of these two happen, if both of them happen, awesome. If either of these two happens, then we are very happy with the quantum solution. So any questions, Sheila? We can keep it a bit interactive. I can pause in between and ask if there are any questions. If you have any questions, we can look into this, or we will just go towards the actual example of the max cut problem.
There are no questions as of now.
Okay, cool. So let's go to the precise problem that we are interested in, and that is called the maximum cut, or in short, the max cut problem. What is the max cut problem? Think of that I have given you a graph and I have given you two colors, green and yellow. You can color any vertex whatever way you want. So that is what we will call as assignment, how you assign the colors to the vertices. But if say take an example that 0 and 1 of the vertex is green, one of the vertex is yellow, I will say that this edge is cut. It doesn't matter in which order. You could have said that, okay, this is yellow, this is green. I'll still say that the edge is cut. What is required is that if for an edge, the color of one vertex is different from the color of other vertex, not in any particular order. On the other hand, 1 and 3 is not cut because both of them are of the same color. Of course, we want an assignment such that the maximum number of edges are cut. Where is this problem useful? Think of, we all are using mobile phones at this point. We all have some, I am using Vodafone. So there is some Vodafone tower from which this is taking signal. Now say for some reason that tower becomes faulty. Will it will my signal cut off totally? No. What will happen? It will take the signal from some other tower. What if this second tower is also becomes faulty? It will take signal from a third tower. What if this third tower also becomes faulty? Now see the point that I am the user and there is a faulty tower from which I could have taken the signal. If a tower is faulty and I am the user, we can consider them, the user and the tower, as two vertices, and there is a connection between them. If I can take signal from that, if the tower becomes faulty, we say that this connection is cut. Right? This is what we say exactly, that the connection has cut. All the telecommunications, see when I was giving this example, one tower fails, possible, definitely. Two tower fails, possible. Three tower fails, okay, seems like too much. At the same time, three towers, four towers, everything is failing. This seems a bit too much, right? Unless there is like a real catastrophe or something. So This is what the telecommunication people really want to know. How many towers should fail such that I will lose signal? The moment I lose signal, there is a customer who is very unhappy, who is very unsatisfied. So they want to maximize the number of cuts here. They want to maximize how many towers should eventually fail so that I lose signal, and this value should be very high. If this value is very high, then it is very unlikely that all the towers fail at the same time. So you see, this max cut problem has a very, very important role to play in telecommunication. Now, remember the first thing that we said, so we understand why this problem is important, but we want to solve this. This is a NP hard problem. This is also what is called an APX hard problem. So what is an APX hard problem? NP hard problem means, again, if there are mathematicians or theoretical computer scientists, don't start yelling at me. NP hard problems, it will require exponential time to solve this problem. Like there is no good solution that can give you, there is no good approach, there is no good algorithm that can give you the perfect solution. APX hard means there is no good approach that can give you as good approximation as you want. Like you may want the approximation ratio to be as high as possible. You may be willing to spend a lot of resource for that. But when a problem is APX hard, there is an upper bound to the approximation ratio that you can achieve using a polynomial time algorithm. If you can go beyond that using a polynomial time algorithm, even then P is equal to N. So max cut problem is not only difficult to solve exactly, it is also difficult to solve approximately with arbitrary approximation ratio. So that's why these are the problems which become very interesting in the quantum domain, right? I mean, that's how that's what I was saying, that you don't want to solve, come up with a quantum sorting algorithm, because we already have very good sorting algorithms. But these are the problems which are very difficult for classical computers to work with. These are the problems which you want to tackle with a quantum computer. Now, remember how we started. Everything that I told right now, I hope you understood what I was saying, but at least you understood what this problem means. You want to assign colors to different vertices. We understand this. A quantum computer does not understand this. So we need to convert it into a language that a quantum computer will understand. Before going to that, we know even a classical computer doesn't understand this. Classical computer understand bits and all. So a classical computer doesn't even understand if you say green and yellow colors, assign all of those. The first thing that we do is we write down the cost function into something that is called a qubit. Now let's look into this particular cost function. And let's say that if my color is green, then I say that the corresponding x is 1. If my color is yellow, I say the corresponding x is 0. Fine. So now let's look into this particular edge, 0, 1. Call this u, call this v. So this is 1, this is 0, and this product is always 0 because one of them is 0. So the summation of sorry, not the summation, the value of this is 1 for this edge. And you can understand that whenever I have an edge which is cut, one of them will be 1, one of them will be 0, and this product will always be 0 because one of these two has a 0 value, right? On the other hand, if I look into this one where both of them are yellow, and I said I'll put 0 here, so this is, both of them are 0, this is also 0, so this is giving a value of 0. What if both of them were green? See, this will be 1, this will be 1, the addition is 2, this product will be 1, and we have a 2 here, so it will be 2 minus 2, and it will be 0. So this expression gives me that the value of this is 1 if the edge is cut as per my assignment, and if the edge is not cut, then the value of this is 0. And we want to sum over all edges, so we know whatever the value of the sum is, that is the size of the cut, that is the number of edges that are cut, right? This is called quadratic unconstrained binary optimization, because there is a maximum of a quadratic term. You don't have anything more than degree 2. This is unconstrained. We will come to this a bit later, but there is no subject to here. This is binary because each of these values can only take 0 or 1. This is binary. Now, the first thing that this is a, so if we think in terms of classical algorithm, we want to maximize this. If I maximize this, then what it means is that maximizing the number of edges which are cut. We want to maximize this. Again, this is not a language that a quantum computer understands. A quantum computer understands +1 -1. Why do we say so? Because in general, if you look into the Pauli observables, X, Y, Z, and everything, if you find out the eigenvalues of any of these observables, these are always +1 -1. Again, physics students, if you are here and want to be too precise, h cut by 2 minus h cut by 2. But anyway, like take that as constant and +1 or -1. So how do I go from 0, 1 to +1 -1? All these values are either 0 or 1. And now I am saying that a quantum computer will understand only +1 and -1. So there is a very simple conversion to do that. Look into this. If z is +1, this is 1 - 1, so x is 0. If z is -1, this is 1 + 1, that is 2, so x is 1. So it is a very easy conversion from x to z. This is in 0, 1 domain. This is in +1 -1 domain. So we write down this with a simple calculation. You can immediately see that if you just put in these values here, it will turn out to be something like this, right? If you have not done this calculation, if this is not obvious to you, I would really go and encourage you that just try this out. This is a very simple calculation, as you can understand. Now, what we see is that we now have a cost function, which is in the +1 -1 domain. All I want is my objective is still the same. Instead of saying that assign zeros and ones, I am saying assign +1 -1 such that the cost function is maximized. Nothing has changed here. But what is quantum here? I mean, this is still classical. What is quantum here? There is nothing quantum in what we just discussed, right? So to make it precisely quantum, what we do is we replace these small z operators with these z operator, this small z, uh, say values with capital Z, which are quantum operators. This is the quantum Z operator. And I'm sure you all are aware of this, that Z is an operator which acting on 0 keeps it 0, acting on 1 keeps it -1. So previously, whatever we were saying that you want to maximize this, find an assignment such that you want to maximize this cost function. The moment we change it into an operator, the same thing we can now say that the objective is find out the assignment such that the eigenvalues are such that this is maximized. Or uh, in the other language, I can say that I want to find the largest eigenvalue of Cz, and when I find the largest eigenvalue of Cz, the eigenvector will give me the proper assignment that I am looking for. Equivalently, what you can say here is, see, identity, half, these are all constant. This is the only variable. When you do some assignments, the only thing that changes is this. So what we can say is, instead of maximizing this, you can minimize only this portion. So you can say that I am minimizing this. The reason often people change it from a maximization problem to a minimization problem is because we have very sophisticated classical algorithms to find the minima. So that's why we often convert it from a maximization problem to a minimization problem. But the idea is the same, that we want to find the largest eigenvalue of Cz, or in this language, we want to find the smallest eigenvalue of Cz or C prime Z. Now a question to you. I'll maybe pause for 5 seconds after posing this question. So what we did, we had a color assignment problem, which was very equivalent to assigning zeros and ones. From there, we are down to a problem where we want to find eigenvalues and eigenvectors. And we know that quantum is very good here in finding eigenvalues and eigenvectors. Question to you is, did I make this problem any easier? I started by saying that max cut is an NP hard problem. It's an APX hard problem, but we did a lot of calculations. And now we are in a scenario where instead of trying to find the assignment, you want to find the largest or the smallest eigenvalue. Now, did this make my problem any easier? Maybe I'll pause for a few seconds and let you think of this. Yes or no? Just answer to yourself. You don't have to answer to me, and then we will tally. If any of you are thinking yes, that's wrong. Why? See, because the steps that I did here was very, very simple. I went from here to here. It's a very simple calculation to go from here to here. And then I replaced the small z's with capital Z's and said that now instead of assigning +1 -1, you just calculate the eigenvalues. I started with a problem which was NP hard. I did 2 or 3 steps of calculations. Now, if this problem becomes easy, and these are all polynomial time calculations, I have not done something very critical calculation. Then I have changed my NP hard problem into a polynomial problem if this is an easy problem. So that's first thing. That's the first reason to believe that I have not made this problem easier by posing it into this language. Second point, if you now think mathematically to what we have, what is the size of the Z operator? 2 cross 2. That's a 1 qubit that's acting on 1 qubits. If you have acting on n qubits, what will be the size of the total operator? 2 to the power n times 2 to the power n. It's exponential in the number of qubits, which is the number of vertices. How many eigenvalues will it have? Exponentially many. So if there are no immediate tweaks and you want to just use a very naive algorithm to calculate the minimum eigenvalue, what will you have to do? You will have to calculate all the eigenvalues, find the minimum out of that. There are exponentially many eigenvalues. It will take exponentially many time. Or for those of you who are from, say, physics or something, you can think that this is basically diagonalization is very difficult in general. So just by posing it into this way, I have not made it any easier. So what do we do when we end up with a problem which is not very easy? What does your teacher do? Or if any of you have taken class and if your student comes up and say that, I am finding this very hard, what do you tell the student? Well, if you find this very hard, so just one last point, this is called the Hamiltonian. So this is converting from Cubo to Hamiltonian. So what we are down here, this is what I'll call as the problem Hamiltonian henceforth. And in general, the problem Hamiltonian, I want to find the ground state of that. I will stick to this notation that I am trying to find the minimum eigenvalue. I want to find the ground state of this Hamiltonian, which we discussed is very difficult. So as I said, that if you are a teacher or if you're a student, most of the time, if you go to the teacher and say that, this sum is very difficult, I am unable to do this sum, the teacher will say that, okay, start with something easier. You start with something easier, and as you try, keep on practicing, you will get a hold of this. You'll be able to solve this also. That's the same thing that we will do here. We will start with a Hamiltonian that I'll call as HM. It's called a mixer Hamiltonian, whose ground state is easy to find. There are no other criteria for this Hamiltonian, how you select this Hamiltonian. The only criteria is HM and HP should not commute with each other. If they commute, there is no phase transition. So because they have kind of joint eigenbasis and all of those things, so there is no phase transition, they should not commute. Other than that, there is no restriction on how you choose HM. You can choose HM in any way as you want, but you want to make it so that the ground state you can find very easily. Now, if we can find the ground state very easily, the first thing that we do is we prepare the system in the ground state of HM. And then, just as I said, that you start from an easy problem and slowly make your way up to the difficult problem, you now evolve the Hamiltonian in this way. So here, as you can see, S is a variable that goes from 0 to 1, When S is 0, you start with HM, which is the mixer Hamiltonian. That's what we said. When S is equal to 1, you end up in HP. And this is what we want. When you start with the ground state of here, and the adiabatic algorithm says that if you start from here, the ground state of HM, if you evolve the algorithm slow enough, then the system will settle down in the ground state of HP. Great. So there is one problem, and that is this phrase slow enough. In general, what is seen is first, it is very difficult to calculate what slow enough means. It is very difficult to calculate. Second, if there are scenarios where you can calculate, often this slow enough is exponential in the number of qubits. Your time should increase exponentially in the number of qubits or the number of vertices. So once more, it's the same rabbit hole that we are down. So what we do is we say, remember, this is how we started by saying that, we are not after the best solution. We are happy with a good enough solution. So what we will do is we will give it a practically acceptable time of evolution. It is not like an infinite time. I'll give it a practically acceptable time of evolution. If you do so, there is no guarantee, just like I said, that if you start with the ground state of HM, you will settle down in the ground state of HP. This guarantee goes away the moment you don't follow this adiabatic requirement. And when this guarantee goes away, what we can hope is if you are still sufficiently slow, not trying to be just too fast here, if you are still sufficiently slow, you will settle not in the ground state of HP, but somewhere which is close to the ground state of HP. And we are happy with that if the closeness is close enough. This is the idea of adiabatic algorithm that can be used to solve this kind of problems. Now, if you have been paying attention, you should have one more confusion here. The confusion is that yesterday, I know you heard of quantum computing, introduction to quantum computing. I'm sure you heard of qubits, you heard of quantum gates, which are unitary operators, you heard of measurement, and you should be thinking to yourself now that, okay, we heard all of those that, you prepare a quantum circuit and you apply all those quantum gates there, you measure things collapse. These are the things that the speaker yesterday told us. And here is this guy who is saying that, okay, you have a Hamiltonian that you evolved. Where is the qubit? Where is the gate? Where is the measurement? True. When I talk of adiabatic algorithms, none of them are there. But we are interested in gate-based quantum algorithms. So what we will do here is something called trotterization of QAOA. So I'm sure many of you are from maths background and you know trotterization. But if there is anyone who is not from that kind of background, or if you want a good analogy, um, you can think of analog to digital conversion. So when I am talking, for example, when I am talking, this sound is analog. It's a continuous sound. On the other hand, when it is going through, say, my laptops and then through whatever channels are there, and you are listening at your end, all of these are digital. So this analog voice cannot carry over. These systems cannot carry this analog voice. It needs to be digital. How do you do that? The first thing that you do is you sample. You sample at many positions. When you keep sampling, what you do is you sample at many positions. You take the values of those samples and you pass it. And if your sampling is close enough, there is still some loss, but you hardly recognize that loss. It is like discretizing this thing, this evolution, this continuous evolution, but in such a manner, in such a way that it's a very good approximation of this continuous evolution. The first thing so that we do, we prepare the system in the ground state of HM that remains here. Now we evolve the system in discrete states. We have this problem Hamiltonian, we have this mixer Hamiltonian, and we prepare a quantum gate, which is a unitary. Now, you can always double check that this HP is Hermitian, HM is Hermitian. And when you take the exponentiation of an Hermitian, it becomes an unitary. Um, if any of you is not aware of that, don't worry. This is a unitary operator. That means it's a quantum gate. So now we have quantum gates. So instead of saying that I am evolving this continuously, you can say I am applying these quantum gates. And you can think of gamma and beta as the time of evolution, which is equivalent to the length of these discrete steps. Now you can ask a different question here. Like there are questions, of course, that are coming from these 3 points. How do you know what is the length of this discrete step should be? It seems that this is what you should be thinking, that this guy has drawn the picture in such a way that it seems that they are getting close enough, not very close, but close enough. But this is what he is showing us. How do I know exactly what is the length of these operators should be, what the value of gamma and beta should be? We don't know. The answer is we don't know. And this is where the variational idea that we started with, preparing a coffee, comes into play. So if I don't know, I will start with a trial wave function with random values of gamma, beta. We will keep on varying gamma and beta. And every time we expect that as we come up with a new set of gamma and beta, we hope that we will get better cut values. So the solution will be better than the previous. And there should be some convergence criteria, like how many times I'll try. If my value is greater than a particular value, if my cut size is greater than a particular value, I am happy. Or if I keep on iterating over new sets of parameters, but it doesn't significantly improve my cut size, then we stop. All these convergence criteria you can put into, but this is basically the idea of what we do. Ideally, nobody said that you need to break this only once. And again, for those who knows trotterization, it's essentially that you have a evolution here. For those of you who know, you have an evolution here. You want to do the exponentiation of this, and you break it down into multiple steps. Um, Smaller the steps, and hence more the number of steps, the better is the approximation, of course. And that's what we are doing. You can take p equal to 2, you can take p equal to 3, p equal to 4. If you can, ideally speaking, take it to p equal to infinity, then QAOA is exactly equivalent to the quantum adiabatic algorithm. That means it exactly traces out the path, the continuous evolution path of the quantum adiabatic algorithm, and we are guaranteed to get the exact solution. But of course, we cannot take p equal to infinity. That's as good as saying that you do the evolution infinitely slow. That's not practical. For some practical value of p, QAOA will settle down to some approximate solution. And since we are doing trotterization, higher the value of p, better is the solution. Closer you get to the actual ground state that we want. But at the same time, we need to remember that when we did p equal to 1, so when I'm doing one step, this is called p equal to 1, two steps of trotterization, p equal to 2. There were two unknowns, one gamma, one beta. Now here are four unknowns, gamma, beta, gamma, beta. There are four unknowns. If you take p equal to 3, there are six unknowns. So you see the number of unknowns that we have keeps increasing as we increase the value of p. So what we have here is a bit of a trade-off. Higher the value of p, the better is the solution. That is mathematically guaranteed. But higher the value of p, two things will happen. We will see how to create the circuit later on. But higher the value of p, first the circuit will be deeper. The more deep the circuit will be, that means it will be more affected by noise. At the same time, higher the value of p, more is the number of unknown parameters. That means the complexity of finding the optimal parameters keeps increasing and increasing as you go to higher values of. So if we understand this, I hope, I mean, I didn't start by saying this, but usually it's good. I really prefer if you just follow on this story along with me. Um, in such a way that you can go and tell your friend like the story, even if you cannot go and tell the exact details of everything, but at least you can go and tell the story. So in general, what is the QAOA algorithm? We start with some random initial parameters, gamma and beta. For some particular p, there will be p gamma and p values of beta, and this is classical. We don't need a quantum computer to create random values here, right? You can just call, say, numpy dot random and something. The next is we prepare the system in the ground state of HM. We prepare the system here. This is quantum, obviously. Preparing the ground state of HM, it's a quantum state. This is obviously quantum. Now we apply this multiple times, UHP gamma and UHM beta, multiple times. This is again quantum, and we get a quantum state. Next, we calculate the expected number of cuts. Remember, this is a quantum system, so the outcome is probabilistic. If I try, say, 1,000 times, the outcomes are not always the same. It's a probability distribution. That means we want to calculate the expectation value of that. And that is classical. Like once we get the outcome of there is no quantumness here. We can just classically calculate the expectation value. And again, we use some classical algorithms to find new parameters, gamma and beta, and we repeat the steps 2 to 5, and we hope that we will get better and better solution. So this is QAOA in a nutshell. And as I started by saying that um, if you go to, say, a quantum chemistry problem, this unitaries will be different. Maybe this will become a UCCSD. If you go to a machine learning problem, this will be perhaps some hardware inspired answers or something. But the overall way you solve any of these problems using a variational algorithm is exactly similar. Now, just to point you out one more thing, as you can understand each and every step here, you can do some sort of research here. Of course, what is a good way of finding HM for a given problem? For MaxCut, I'll show you. But if I ask you for a different Cubo problem, what is a good HM? How do you find good HM? How do you prepare this circuit very efficiently? Do you have to start with random initial parameters? Because you can understand that the more you repeat this 2 to 5 steps, the more time you need. That's kind of the classical bottleneck here. So do you need to start with random parameters, or can you do some better guess? There are many research that has been done and ongoing around what is called the convergence of parameters for QAOA. And using that convergence, people are coming up with machine learning algorithms that for a given graph can give you a very good initial parameter so that the number of iterations that you need is quite minimal. So as you see, and of course, there are many nice algorithms, classical algorithms here, but people are also trying to improve these. All the steps, if you understand all the steps, you will see what are the bottlenecks of each steps, what are the limitations of each step, and there is always a research scope for any one of these. You can take it up and try to improve on top of this. Okay, maybe I can just pause again for some time. If you have any questions, maybe put it in chat or unmute and ask however it suits.
There's a question that what is the correct approach for physics students to visualize the complex mathematics of optimization problems? And they also want you to tell about uncertainty and probability theory.
Okay, let's come to that later because that's not related to this. I mean, the optimization is, but let's come to, okay, please just remember that question and make sure to ask once we end. Okay, let's complete this and we will see. Now, here is one thing that is very important to understand. Yeah, this is really important to understand. The problem that I talked of, max cut, was an unconstrained problem. I kind of said it's cubo quadratic unconstrained binary optimization. What does it mean to be unconstrained? Let's think of how to say. Let's think of this. I asked you that you want to color the vertices using yellow and green. You want to assign some colors. Say you color all the vertices with yellow. Is it a wrong solution? think to yourself, give it a moment or two. Is it a wrong solution? The answer is no. Is it a bad solution? Yes. None of the edges are cut. It's a very bad solution. But is it a wrong solution? No. There is nothing called a wrong solution when it comes to an unconstrained optimization problem. Think of max cut here. When you think of max cut, there is nothing called a wrong solution. A solution is either good or bad, but it's still a solution. If you put everything as yellow or everything as green, it's still a solution whose cut size is 0. Fine. But there are many real world problems which are constrained. So, for example, let's say, when the organizers were assigning speakers, let's say I go and say that, um, so I'm talking today. I think today is Wednesday. Yeah, let's say if I would have gone and told them that I don't talk to people on Wednesdays. I don't like talking to people on Wednesdays. So put me somewhere else. Maybe someone comes and tells that, oh, you have put Ritojit on Tuesday. I don't like Ritojit. I'll not be in the session where he is. So these kind of things. Now, if the organizers put me on Wednesday, that's a wrong solution. If the other speaker who does not like me, maybe if they put both of us on the same session, that's a wrong solution. So there are constraints. Previously, we were thinking of that I want to maximize Cx. Now I would have a constraint subject to that there is some constraint over each of this xi. Maybe some values that xi can take or it cannot take. And a very classic example is maximum independent set. So it's defined as that it's a graph G equal to VE, where you want to find the largest set S. It's a subset of all the vertices such that no two vertices in S are neighbors. So the vertices in S don't like each other. They are not neighbors. So now see, if you create a solution where there are two neighboring vertices in S, this is a wrong solution. So whenever we come to a constraint optimization, the first question that we will ask, is your solution correct? Then we will ask how good your solution is. And this makes this type of problems way more difficult. Now, how do we associate this penalty? Because we have seen how to take Cx, write a cubo corresponding to it, then from there go to Hamiltonian, then from there do trotterization. We saw all the steps. But the moment you have a constraint, what you can do is you can add a penalty. It's kind of this Lagrangian method that you have. You can add a penalty using the constraint here. If you don't want to think of this so mathematically, you can try to think of it that say the example that I was saying that there are two speakers, me and someone else, and we don't like each other, so I don't want to be in the same session with that speaker. I will not say don't put our both of us in the same session, but if you do put both of us in the same session, I will become a very difficult speaker to deal with, something like this. So it's kind of saying that, okay, instead of directly saying that you don't do this, you have to follow this constraint, you can say that if you don't follow this constraint, there is a big penalty that you have to pay. So what we do here, instead of putting this as a cost function and a constraint, you take the constraint and you add it to the cost function with a very big penalty. And again, mathematically, this is the Lagrangian model that you can think of. Now, there is one big issue here. When I first talked of, if you remember the way I defined HM, I said that the only requirement was HM and HP should not commute with each other. If they commute, there will not be the phase transition, that the ground state will not transit from the ground state of HM to the ground state of HP. But the moment we have this kind of constrained optimization, we need to be very careful of HM. Of course, we need it to be as simple as possible. We need that it should not commute with the problem Hamiltonian, but at the same time, it should also map a valid solution to another valid solution. I cannot start with a valid solution. I cannot start with a solution which is a independent set and then I put an HM, it creates a superposition where some states are independent set, some are not independent set. This cannot happen. So it should map a valid solution to another valid solution. This makes this a way more complicated problem. See, what it means is that when you create UHM beta for any value of beta, this cannot violate the constraint. If you start with a state that does not violate the constraint. And this is what makes things way more difficult. And if you look into the mixer Hamiltonian of the maximum independence set, let's not try to go into, let's not try to go into every intricate detail of this. But what it is doing is that it first checks. So say I want to flip the vertex I. If I want to fix the vertex, flip the vertex I, that means apply Qiskit, change it from 0 to 1, something like that. If I want to flip the vertex I, that means say if the state is 0, it is not in the maximum independent set or in the independent set. If it becomes 1, it is in the independent set. So when you flip it, you need to be aware that none of the neighboring vertices are in the independent set. This is what this second part is doing. It is ensuring that when you are going to flip, you will flip vertex I only if none of its neighbors are in the independent set. And when you have systems like this, usually the problem is more complicated, the corresponding circuit becomes more complicated. So you need to be aware of that. And it's again a big area of research. How do you come up with good HM here? And how do you build good circuits from this? So just to give you, going back from maximum independent set to max cut, that this is the focus that we want to have. To give you a flavor of how do you create the circuits just from this algorithm. See, what we want to do, what is the first quantum step? I want to prepare the ground state of HM. What is my HM for max cut? I usually take it as sum over Xi. Now, if you see sum over Xi, what is it doing? Remember that the problem Hamiltonian was Zi Zj. So Xi anti-commutes with it. What is the ground state of Xi? If you remember, the ground state of Xi X is plus, which is this 0 plus 1 over root 2, and this goes for every vertex I. So you want to prepare every vertex in this particular state. On a quantum computer, we always start with the state 0, and we can go from 0 to plus using the Hadamard gate. So it is as simple as that, that you start with, this is my particular graph. I have a vertex associated with each of these, and I apply a Hadamard gate on all of them. You cannot have anything simpler than this, right? We wanted to make sure that finding the ground state of HM is easy. We here have a depth 1 circuit. You cannot have anything simpler than that. Just apply a single gate on each qubit. Now we need to prepare this UHP gamma and UHM beta. So how will UHP gamma look like? Stay with me for some time. This will immediately look a bit complicated, but it's not. So stay with me. What was my HP? Sum over Zi Zj. It was ideally identity minus Zi Zj, but we said that we, instead of trying to maximize identity minus Zi Zj, we can try to minimize Zi Zj, right? So we will deal with this. What is UHP gamma? It is the exponentiation of this. It is the exponentiation of minus I gamma HP. Now, if you just write this down, it is exponentiation of minus I gamma. This is HP. And again, for those of you understand this, you see all of these terms commute with each other. So you can just take this exponential and write it as the product of individual exponential sums, since they all commute with each other. So I can take the summation, which is in the exponent, I can take it out, it becomes a product of each of these individual terms. And each of these individual term is an RZZ gate. This exponentiation of minus I gamma ZU ZV, it's an RZZ operator. Where should we put the RZZ operator? For every edge, UV. So if you look into this circuit, we have an edge between 0 and 1. I have an RZZ operator. This is how Qiskit represents RZZ. I have an RZZ operator between 0 and 1. I have a edge between 1 and 2. I have an RZZ between 1 and 2, and so on. Right? So we have the UHP gamma portion. Now, the third thing we need is UHM beta. We have already seen this is HM. How do we do UHM? Take the exponentiation of this, and this is how the exponentiation of this occurs. And once more, we have e to the power minus I beta sum over xi. These terms commute with each other, so I can take out the summation, write it as a product of individual terms. Strictly speaking, the way Rx gate is defined, it is Rx gate is defined as exponentiation of minus I beta over 2 by xi. Those of you who are knowledgeable in quantum computing, you will understand, because in density matrix, the amount of rotation is twice the size of the angle. So strictly speaking, this should be Rx2 beta. But anyway, let's not worry about that. Now the question is that where do we put this Rx gate? On each qubit I. So we have this Rx gates on each qubit I, and we are done with the circuit. This is for p equal to 1. If you have p equal to 2, the state preparation happens only 1. If you have p equal to 2, the same part will be repeated twice. If you have p equal to 3, this part will be repeated thrice, and so on. So it's very simple to come up with the circuit of this max cut. And in fact, if you know the QBO of any particular problem, if you write the Hamiltonian, you can see you can just make this similar kind of argument, and you can come up with the circuit. Coming up with the circuit from this is very simple. This is where I want to end. But before I end, see, you guys are in one of the best institutes of our country, and some of you asked that how should I start understanding this complex thing of optimization, combinatorial optimization. Uh, there is an archive paper on how to write QBOs with more mathematical explanation on what the matrix, vector, and all of those looks like. You can just search for it. It's kind of a formulation of QBOs for many different problems. Look into some books on combinatorial optimization. It is not very easy, not very difficult. The way you should be thinking, again, if you are physics students or chemistry students, the way you should be thinking is that instead of saying, when I say it is, say, sum over Zi Zj, it's kind of an Ising model that I am thinking of. There are some magnetizations here. So if you understand Ising model, you understand combinatorial optimization. They are the exact same thing. There are some very nice papers. There is a guy called Stuart Hatfield. If you look into his PhD thesis, he did an extensive study on particularly QA/OA for constraint optimization problem. The unconstrained one was given by Farhi. The constraint optimization problem, he did a very exhaustive study, and his PhD thesis is available. He was in University of Columbia. I think he's in NASA now, in case unless he has changed. He's in NASA. Um, his PhD thesis is publicly available, and he has done a very nice job in explaining all these steps for different problems, not only for a single problem, not only for maximum independent set, but for many other problems that there are. So what I was saying is, I want to end it with a challenge for you all. And I really hope that you, at least some of you, will take up this challenge. This Given that as I said, given that you are some of the best students in our country, I talked about a very particular problem today. This is not the only combinatorial optimization problem, right? MaxCut is not the only combinatorial optimization problem. There are many of them. Use this thing. Let's think that you want to design this package. This is a package which will be a combination of many combinatorial optimization problems. Make up a group, and you will see it will help you with the study. It will help you with understanding the problems. It will help you with coding. It will help you stand out. So just to pitch, um, perhaps many of you know, if you don't know, the things for 2026 is the call is already open for IBM internship for summer 2026. And many students come and ask that what should we so what should our CV look like and everything. Now see, we have so many things. We have the Qiskit Global Summer School. We have the learning platform. If any of you are new, just go to the IBM learning platform. There are awesome tutorials, awesome courses there. Um, Follow those. Everything is for free out there. Um, but what I want to point out here is every student is looking into this Qiskit Global Summer School. India is one of the largest audience that we get in Qiskit Global Summer School. India is one of the largest users of Qiskit. India is one of the largest user of the open plan of 10 minutes. If you are not using it, please go and use and uh, try to find out for yourself how much work you can still do on 10 minutes. Um, India is one of the largest users of those 10 minutes. So many fall fests are happening every year. They are hearing from some of the top researchers and people. All the students are listening to that. When you apply for internship, when you apply for job, how do you stand out? How do you show that you know something more than what everybody now knows? So this is a challenge that I have for you. As I said, I hope some of you will take it up and reach out to me in say 6 months or 1 year. This is not a 1 day or 1 week challenge. So I hope that you guys really do reach out to me once you start doing something on this. Pick a few problems. Say pick 4 or 5 problems. Make a team of a few people. Pick 4 or 5 problems. Study those problems, create a package. How the package will be? A user comes and the user will tell me that, okay, I want to solve problem number 2. Say problem number 2 is max cut, just for an example. I want to solve max cut. Here is the graph for the corresponding problems. And you can ask that, okay, how many number of iterations you want, all these things you can ask, and whether you should run it on a simulator or hardware. With this information, create the Hamiltonian yourself. You see what this shows, if you can do this on a code, it shows you understand the problem very well. If you don't understand the problem very well, you cannot just take a problem and on a code generate the corresponding Hamiltonian. From the Hamiltonian, you construct the circuit. That means that all the steps that I was showing you how to go to the circuit from the Hamiltonian, you understand that very well. There may be circuit specific optimizations. Some of my PhD works that I did, say roughly 3 years back or something, used that all the examples that I showed you how to create the circuit for max cut. There are many things that you can do to further optimize that circuit, remove some of the CNOT gates from there, from the decomposition of the RZZ operators. A lot of things you can do. This is only what I did was only for max cut. There may be similar optimizations possible for maximum independent set. It can be a different optimization. It can be similar. It won't be exactly similar, that I can guarantee. But it's not impossible to come up with certain solutions like that. So there are scope of research also. Like how do you do this circuit specific optimization? This will vary from problem to problem. And these are very rich algorithmic studies. I mean, I can tell you from my experience, I proposed 4 algorithms for this kind of optimization only for max cut. And I was very happy with those algorithms. And they are again together with the IBM India team. So I was very happy with those. Anyway, similarly, if you look into all these problems, you can similarly come up with novel algorithms for optimizations. Now you do transpilation. There are transpilations which are specific to problems. There has been some studies from IBM where you can actually improve the transpilation for max cut problem by using this SAT, the satisfiability kind of problem, instead of just naively using the transpiler that Qiskit provides. So you see, there is a scope of research here also. How do you can you do better transpilation for the problem that you want? So given a problem, how do you create Hamiltonian? Of course, there are many defined problems, but there are still many undefined problems. There has been a recent paper from IBM along with many institutes and industries. It's called, I think, benchmarking the or something on optimization decathlon or something. I have forgotten the exact name, where all these people have identified some of the most important problems that combinatorial optimization people should be tackling. So look into that paper and also look into the classic problems that are there in different domains like VLSI, all this route optimization and everything, all these kind of problems. Take some of those. What if you do this, what it shows is step one, you know how to create Hamiltonian. You can go from a problem, you can do the mathematical formulation. Then either you just follow normally, you don't have to do a research on every step, right? You either you follow all the steps what Qiskit is providing, or you can even do optimizations here, you can do improvements here. As I said that uh, possible to do improvement here, possible to do improvement here, all these things are possible. It shows how well you know the problem, and then the final result you show to the user. What it shows, what it makes you stand out is you understand the problem, you understand the mathematics, you understand optimization, you understand Qiskit coding, and you can create packages like this. You can do state of the art coding at the industry level. Think of this, that if you have built up a team and you do something like this and then you go to the job market, versus if I go and say that, I have studied some QAOA problem, I know how to do combinatorial optimization, I have done some Qiskit codes. Who stands out? Who gets the first opportunity to do this? And if you really do this, I hope you do this, make it in such a way that, see, it is not possible for you alone or a group of you to just keep putting in problems and problems. You keep solving problems here, right? Make it in such a way so that others can come and contribute. Maybe you take 3 or 4 problems and you do this kind of thing. I come up and put a fifth problem. Your software should allow me to do that. Your software, if I come and say that you have taken problem 2, I have a better way of transpilation of that problem. Your software should allow me to put my own transpilation here. The moment you do that, take some time to do this, it shows that you can write codes at the industry level. You stand out. So if you go and show this, that this is what I have built, and you can build on top of this, you help the future students also. They can use this tool. You help yourself stand out when you apply for jobs or internship, and you help the community. You help the upcoming NQM. All these 100 algorithm calls that have been made, and people will be coming up with algorithms. And the last thing, this need to not be for combinatorial optimization alone. I am telling you is this in terms of optimization because I talked of optimization. If you are interested in chemistry, go ahead and make something like this in chemistry. If you are interested in physics, go ahead and make for physics. Machine learning, go and make something for machine learning. But do something. I mean, if you really want to stand out, make it, do something like this. Take this idea and build on top of this. Maybe you will come up with better ideas than what I am showing you here. But at least do. I mean, don't just say that I have learned these things, but show something like this and just stand out. So yeah, lots of talking. I'll stop here. And if you have questions, comments, we can take that.
So there's a question. So how can we optimize NP-hard problems using quantum principles since we have the operational efficiency of quantum?
Sorry. Can you just repeat the last thing once?
So the doubt is that we have the operational efficiency of quantum. So how can we optimize the NP-hard problems using the quantum principles?
Okay, two things here. First, there is no guarantee that P is not equal to NP in quantum. There is no guarantee P is equal to NP in quantum. No, there is no proof that P is not equal to NP even in classical. But when it comes primarily to this kind of QAOA problems, the goal is not to show that you can outperform classical algorithms in terms of showing P is equal to NP, but often the goal mainly is to reach a good enough solution faster than what classical is doing. So most of the time you will see that the goal here is not try to outperform the quality of solution that classical is already giving, but maybe reach the same quality faster. I hope that answers.
Yes, certainly. So with this, we come to an end for the day two. Thank you, Ritajit, for the brilliant session on variational approaches for quantum optimization. Your insights into hybrid quantum classical methods and real-world optimization challenges truly deepened our understanding. The audience loved the clarity and practical perspective you brought. So it was indeed an inspiring close to day two of the Fall Fest. And a huge thank you to Shraddha and Ritajit from IBM Quantum for their incredible sessions. From fault tolerant quantum computing to variational optimization, today's talks truly showcased the depth and promise of quantum research. We're grateful to all the participants for the thoughtful questions and enthusiasm throughout the day. Stay tuned for the day three. And thank you, everyone.